This video is in continuation of our previous video, which was about first order numerical differentiation. This is about second order numerical differentiation. Before going forward, let's have recap of what we have done in the previous video. We have studied about the Taylor series and developed the formula for the forward difference approximation, backward difference approximation, and central difference approximation for the first order. And now we will going to study the differentiation or the numerical differentiation for the second order. But before going to the development of the formula, we will have some recap of what we have done so far. So first, we studied about the Taylor series and Taylor theorem. Theorem just says that any smooth function can be written in the form of polynomial, and series gives us the way to write that function. And we have learned that if we have smaller spacing between x and x naught and more term, then there will be good result or good approximation of the function. So for the simplification, we can write this the above Taylor series in this form as well. And using this form, we developed the forward difference formula, the backward difference formula, and the central difference formula. Remember that H is the step size here. And we computed and solved example, also computed the accuracy of these methods. So now we will develop the formula for the second order, and again we will use the Taylor series in that. And for development of the second order formula, we will write the function Taylor series of the function f of xi plus 2 in term of f of xi. We know that when we write the function f of xi plus 1 in term of f of xi, then there is a term h appearing in almost every term with power, some power. So this h is the difference between xi plus 1 and xi. When we are thinking to write the Taylor series for xi plus 1, then we can see that the difference between xi plus 2, sorry, xi plus 2 and xi is 2h. So each h will be replaced by 2h in the above formula, because here we are writing it for xi plus 2. So each term having h in the above expression is replaced by 2h. So here are the two expression fxi plus 2 and fxi plus 1 in term of Taylor series. So what will happen if I multiply second equation by 2 and then subtract it from equation number 1? So I'm going to get a 2 here, a 2 here, a 2 here, and a 2 here, and there will be a minus sign as well. So if I have this thing, so I can see that I'm going to get this thing, that it will be f of xi plus 2 minus 2 f of xi, because I have multiplied it with 2. Here I'm going to get a minus f of xi. Here we can see that there is a 2h, there is a 2h, and this 2h here, and there is a minus sign, so this term will cancel out. And similarly, we can see that there will be a 4 if we open the derivative, open this power. So 2 factorial is 2 and 2, so I will left with 2h square in that case. And here if I multiply it with 2, here is a 2, here is a 2, so I will get only a negative f double dash xi here. So if I simplify this, I'm going to get f double dash xi h square. And from here I want to get expression for this term, so I will take this term to the other side and then divide it by h square. I'm going to get I'm going to get this kind of an expression, and you will see that the order of the array term again depends upon the edge. So we have developed the formula for the forward difference. Here you can see that present value and two of the future values are used, whereas we can develop a similar technique to calculate the backward difference formula, where we have present value and two of the previous values, and similarly we can calculate a central difference formula with current value and one value from the previous value and one value from the forward value, and structure of the formula is bit like the same. And we can see that order in case of forward and backward difference depends upon h, whereas order in case of central difference depend upon h square. This can be proved, and we will going to prove it in the next slide. We know the expression of the Taylor series in the form of Taylor series of f of xi plus 1 and f of xi minus 1 is given here. If I add these two up, I'm going to get f of xi plus 1 plus f of xi. So this term is going to be twice of f of xi. This will be cancelled, and I'm going to get f double dash xi here, and the order containing h power 4 and higher terms. So I can simply write this as in this form. So here I'm using a future value, a previous value, and a present value. So this central value have a minus 2, just like in the previous formula. You can see that in all these previous formula, this middle value is having a 2 multiple here, and there is no 2 in the denominator of the central formula. So with this, we can solve an example. If we are given with the t and distance covered in meters here, and we are asked to find the acceleration of the runner, and we know that the acceleration is given by the double derivative of the distance, and the formula for the double derivative is for the central difference case is that f plus h into this is the this is future value, this is the present value, and this is the past value. So I have t is equal to 1.5. So if I use this here at 1.5, h is, what is the difference between any two consecutive term? H is 0.5, so h square is 0.5 square, and I will have to write f of e plus h mean f of 1.5 plus h, which is zero point 0.5. So f of e plus h is going to be 2. Then f of a, which is 1.5. And according to formula, we have to multiply with minus 2. And then f of a minus h, which will be the past value. So I have to use the value 2 from the table, I have to use the value of 1.5 from the table, and I have to use the value of 1 from the table. And by inserting this value here, I'm going to get the answer. So it is just the simple thing to calculate, and we can do some more examples. So using the technique which we have developed, we can calculate the second difference for the given function at x is equal to 2.5, and h in this case is given as here. So this is the data given to us, and this is the formula which we are going to apply. So when we apply this formula, it is 1 over h square, h is 0 0.1, so 1 over 0 0.1 square into f of 2i, which is a future value. I want to calculate it at f of 2, so future value with the difference of 0 0.1 will be 2.1. So f of 2.1 minus 2 into f of the value where I want to calculate this, and a previous value, which is 1.9, because it is x minus a minus h, or a is 2 and h is 0 0.1. So 2 minus 0.1 is 1.9. So from the table, I can get the values and I can multiply or and subtract and do the current operation. I can get the answer, which is equal to 2. 29.593200. For the same, I can I can get a value of 2.29.704275 if I assume h to be zero point 0.2. So it is an important work to do if we compare the error between h of zero point 0.1 and h in case of zero point 0.2, and using the same formula, then we can repeat the exercise with the forward difference formula and repeat the same exercise with the backward difference formula to completely give the formulas and their uses, and you can verify which one is the best. uh, to let you know which is there are different formulas available for the first derivative, for the second derivative, and it depends upon their error. So uh, it is not only the formula which we have studied, but this is not part of our course. I'm just mentioning it to develop your interest that we have used this for the difference forward difference formula and this as a backward difference formula, but there are some other expressions which have the higher accuracy than we have studied. So how to develop this formula is an interesting area of research. So backward difference formula for the first derivative, and another form of the formula for the first derivative, which is more accurate. So how can we develop this formula is a good exercise, but it is not part of your course. So I'm just informing you about this, that there are different formulas available, but you will do what you are taught to in this video and the previous videos. Thank you very much for your attention.